drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hi friends, welcome back to the course on Introduction to Material Science and Engineering offered by Edupedia World. Today we'll continue our discussion on phase diagrams and concepts of phases, which we have been discussing for several lectures now. Let's see. The free diagram for the eutectic system, like the one we saw for the isomorphous system. Here too we will take 5 different temperatures and try to plot. To begin with, we are at very high temperature T1. At very high temperature, what will happen is liquid will have minimum free energy, thereby for all composition will get liquid as the stable phase. So here we get all liquid. As we lower the temperature, what will happen is first we'll hit the melting point, but we are not taking the melting point, we are going further lower at temperature T2. What will happen is that for a particular regime we'll get beta, which is the most stable phase. Beta is lower in free energy throughout this. Till here beta is the lowest energy phase. From here till here the tangent has the lowest energy phase, therefore we will have beta plus liquid, and over here, over the remaining region, liquid is still now the lowest energy phase. So let's see, temperature T2, till here we have solid beta, then we have liquid, solid liquid plus beta, then we have the liquid, right? Next we take temperature T3. In temperature T3, what is happening is beta is of the lowest free energy for certain region, then we have liquid plus beta because the combination has lower free energy than any individual phase. Then we have some region which has the liquid as the minimum free energy phase, but we also have got here alpha, which is the minimum free energy for certain region, and then alpha plus liquid. Okay, we got alpha plus liquid. So let's replicate it here. T3, we come T3, so beta plus liquid, alpha plus liquid, alpha. Now let's go to eutectic temperature, TE. At eutectic temperature there has to be an invariant point, that is a point where 3 phases will coexist. I forgot to mention this, but at this eutectic temperature, eutectic composition, we have 3 phases coexisting. Let's see. Beta stable, liquid plus beta stable, alpha plus liquid stable, alpha stable. And this point, at exactly this point, all the 3, alpha plus liquid plus beta is stable. It's just a singular point. Let's draw it here. Beta plus liquid, alpha plus liquid, meeting point liquid plus alpha plus beta. Finally, at any temperature below the eutectic temperature, we'll have stable beta, stable alpha, and stable alpha plus beta. Nowhere does liquid have minimum free energy. Independently or in combination, liquid does not have free energy which is minimum at this temperature. Let's plot that. T4, beta, alpha plus beta. Okay, so using different temperatures, free energy at different temperatures, we found out which phase is stable for what composition range. We plotted that, and combining all the temperature information, we got the phase diagram for a eutectic system. Just to round it up, this is the invariant point which has 0 degree of freedom and where 3 phases coexist. Okay. One important thing is that in a phase diagram, if you draw an isothermal line, anywhere in the phase diagram, isothermal line, you will always attain alternating regions of single phase and double phase for a binary phase diagram. Single phase alpha, double phase alpha plus beta, single phase alpha. Try to draw it here. What do you get? Alpha, single phase, double phase, single phase liquid, double phase liquid plus beta, single phase beta. It will always happen. If this is not happening, you have not drawn the phase diagram correctly. Okay, so this is I guess more than enough for eutectic systems. We might revisit this when we discuss about iron carbon phase diagram, or at least we will see the eutectic reaction taking place in iron carbon phase diagram later. Now, apart from isomorphous system and eutectic system, we have other systems also which has intermediate solid solutions. In the eutectic system, what we saw, we had terminal solid solutions. There was alpha at one end, beta at other end. But there can be systems like zinc copper system. This is zinc copper system which has intermediate. This is the terminal solid solution alpha, and over here there is another terminal solid solution, but in addition to them you have beta, you have gamma, delta. So there are multiple solid solutions which do not lie at the edge, right? So these are called intermediate solid solutions, and this type of diagram might look quite complicated, but the basic fundamentals, how they are made and how information can be extracted from this, are the same. Then we again have something which is known as a intermetallic compound. Till now what we have seen is any phase which existed in a phase diagram was a region, like it was either a region alpha or a region liquid. We had alpha plus liquid region. But it can so happen that instead of a region, it forms a line compound. That is, it forms a compound which does not lie in a region, but it is a singular line. It is only at a specific composition rather than a range of composition. Here it is. This at around 81%, what we have is Mg2Pb in magnesium lead phase diagram. This is a singular line, right? It is not an area. It has a fixed composition, and this type of compounds which are formed in a phase diagram which do not occupy an area are known as intermetallic compounds. So a point to take home here is that this is considered as a single phase region, though it is a single phase line. Why do I say this? I say this because when you try to see the alternating single phase, double phase, if you do not consider this as a region, then what will happen is single phase, double phase, again double phase here. So this is actually a single phase region when checking if your phase diagram is correct or not. But in reality, this is a singular composition compound that is formed, and it is termed as intermetallic compound. So in reality, what is happening? Single phase alpha, double phase alpha plus intermetallic Mg2Pb, then single phase Mg2Pb intermetallic, then dual phase liquid plus Mg2Pb, and finally over here we have a single phase liquid, right? So what we have seen in today's lecture, let me recap briefly. We started with discussing what is a eutectic system. We saw a eutectic reaction and how does the eutectic reaction take place. We saw the eutectic phase diagram. Then how do we get the eutectic phase diagram from free energy considerations? Now we saw there are intermediate solute solutions In addition to terminal solid solutions which we saw in eutectic phase diagram, then we also have intermetallic compounds in phase diagram, which are not really areas in the phase diagram, rather they are singular lines in the phase diagram. With this, I will conclude today's lecture. Next lecture, we will further our knowledge on phases and phase diagrams. Till then, have a great day. Goodbye.